Today we will discuss about the Cayley theorem. So this is very important theorem in modern algebra. Cayley theorem. So the statement of the theorem is every finite group is isomorphic. Finite group is isomorphic to some permutation group. To some permutation group. Now we shall prove this theorem. So we write down let G be any finite group having the finite number of elements. So we already proved the finite group. So G be any finite group if we take A, an element which belongs to group G, so then for every x be element which is in also G, so then the product, that is AX, is also an element of G. So we consider a function, which is FA defined from group G to group G, such that f of AX is equal to AX. So here for every x belongs to G. Okay, so when G is a group, so we follow the closure property also. A belongs to G, B belongs to G, so AB also belongs to G. So now, so when we define this function, so first we shall prove that this FA is one function. So now first we show that FA is one. For showing FA is one, so we take two elements. So let X and Y be two element of G. So we can write such that FAX is equal to FAY. So FAX equal to FAY. So by the definition, you can write down as FAX equal to AX. So this can be written as AY. So we write down using the definition. So by definition, so AX equal to AY. So we use the left cancellation law. So by left cancellation law, which can be written as x is equal to y. So when x equal to y, so it means that function FA is one function, is 1 Now after proving one function, so we shall prove the FA is onto function. So we can say that a one onto function is possess the inverse only. So FA is onto function. So here we prove that F is onto. So we take the element of set B, means this group. So we take the element of this. So we take the element of this group. Now to prove that the element which belongs to this. So let Y be the element which belongs to G. Y be the element which belongs to G. Y means here we are considering as AX. So AX which belongs to G. So then there exists an element, there exists an element. So which elements? That means which is A inverse into Y is also belongs to G. Means first G. So you can identify both G. So here we take as this is our G, or for second we can consider the another color. So this is. So now we take as this G, and for first one we write down the this one. So now we write down as such that F A inverse, F A inverse into Y, F A inverse into Y. So this can be written as F A. So can be written as A into X. X here we replace X Y, A inverse Y. So this can be written A into A inverse Y. So this can be written as A into A inverse into Y is equal to Y. So this Y, we have taken the element of G, this G. So that means FA is onto function. So FA is onto function. So hence FA is onto. So we basically we consider as AX is equal to Y. So here X is equal to A inverse into Y by multiplying the A inverse both side. So now we show that FA is 1 1 and FA is onto. So we can say that FA is a permutation. So FA is a permutation because we have the statement every finite group G is isomorphic to some permutation group. So first we show that F is a permutation. So permutation we require 1 1 and on 2. So F is a permutation. So let we define a group G dash. So G dash is defined as FA such that A belongs to G dash. A belongs to G dash. So to prove that G dash is a group. So here we are going to prove G dash is a group. So for proving the group, we satisfy all four properties. So first property, we have closure. So first property, we show closure property. So we take two elements. So element in this form, FA. So we take two element FA and FB, which belongs to G dash. So then we can write down as FA into FB. So we operate X. So this can be written as, you can write down this as, so this equal to FA into FB into X. So FB into X by definition, you can write down as BX. You can write down BX. So by definition again this can be written as ABX. This can be written as ABX. Or this we can write down as AB into X. So AB into X. So here we can say that satisfy the closure property. So you can write down this as by definition again FAB into X. So FA into FB into X. So this is FAB into X. So this means function is satisfy the closure property. So that means we can write down as A and B belongs to G, so which imply that A into B also belongs to G. So closure satisfied. So you write down closure satisfied. So after satisfying the closure property, we shall move to the second property, that is associative. So second property is associative. Associative property. So let we take as three elements. So FA, FB, and FC. Be three element which belongs to G dash. So then we write down as FA into FB into FC is equal to FA, or for using this bracket we can write down as FBC. FBC. So this is equal to FA, or FBC this is equal to BCX. So we are going to write directly. So this can be written as BCX. So we are writing directly. So this can be written as A into BC. You write directly. So this by using the associative property for AB, so can be written as AB into C. So this can be written as FAB into FC. So FAB into FC. So we can write down this as FA into FB or into FC. Okay. So for every, you can write down as A, B, C belongs to G. So associative property also hold for group G. So we can say that FA, FB, FC satisfy the associative property. So associative satisfied. Associative satisfied. Okay, so we write down directly with the help of definition. So now we shall prove for the identity, existence of identity. So existence of identity. So here we take since E be the identity element which belongs to group G, because G is a group, so also exists the identity. So it means that FE belongs to G dash, because G dash be also a group. So FE belongs to G dash. So we are going to prove G dash be a group. So this can be written as FA into FE is equal to FAE. FA into FE is equal to FAE, or FAE can be written as FA, because AE equal to EA equal to A when G is a group. So G is a group. So satisfy the identity. So this can be written as FA. So similarly, we can write down as FA is equal to FEA is equal to FA. So means FE. So here FE work as a identity. So FE is the identity element. FE is the identity element of G dash, group G dash. That means G dash. So FE is the identity element of G dash. Now fourth we shall prove that the existence of inverse. Existence of inverse. So after proving the existence of inverse, we can say that G dash be a group. So existence of inverse. So we take as let FA be the element of G dash, where A belongs to G. So which imply that when A belongs to G, the A inverse also belongs to G. So A inverse also belongs to, because G is a group. So then we can say that FA inverse also belongs to G dash. So FA inverse also belongs to G dash. So such that, so when we write FA into FA inverse is equal to FA into A inverse by definition. So this can be written as FE, because we know that A into A inverse is equal to A inverse into A equal to identity. So we can write down as FA to the whole inverse is equal to FA inverse, which belongs to G dash. So it means that G dash is a group. So means inverse satisfied. So hence G dash is a group. So when G dash is a group, so now we shall prove G is isomorphic to G dash. So to prove that, the final part. So to prove that G is isomorphic to G dash. G is isomorphic to G dash. So we define a function. So we define a function phi from group G to G dash, such that phi of A is equal to FA. for every A belongs to G. So A be the element of G or FA be the element of G dash. So for proving isomorphic, so we shall prove that function is 1, 1, onto and homomorphism. So first we shall prove that function is 1, 1. So phi is 1, 1. So for proving 1, 1 function, so we take two element A and B. So then we can write down a FA equal to FB. So phi A equal to phi B. So it means that FA is equal to FB by definition. So FA equal to FB. So this you can write down as FAX is equal to FVX. So by definition, so this can be written as AX is equal to BX. So here we write down as by definition of function. Previously we have defined. So AX equal to BX. So by using right cancellation law, this gives us A equal to B. So by right cancellation law, A equal to B. So means both element A equal to are same. So that means function is 1, 1. Function is 1, 1. So now second part we shall prove that function is onto. So for proving function is onto, so let we take the element of this G dash. Let for FA be the element of G dash and A belongs to G. So such that phi of A, phi of A is equal to FA. So when FA belongs to G dash or A belongs to G, so phi of A equal to FA. So hence we can say that function is onto. So function is onto. So now third or last we shall prove that function is homomorphism. Function is homomorphism. So for proving phi is homomorphism, so we take as phi of AB equal to f of AB. So phi of AB equal to f of AB. So this f of AB for proving homo, so it can be written as FA into FB. So when FA into FB, so by using the definition of function, can be written as phi of A into phi of B. So phi of A into phi of B, so this we can write down by using the definition. So hence we say that function is homomorphism. So function is homomorphism. So when function is homomorphism, so then we can say that G is isomorphic to G dash. So this is the proof of the Cayley theorem.